How to choose coordinate axis. Whenever we solve for an object's motion, we have to set up a coordinate system. And while studying mechanics, we see plenty of examples like that, where the x-axis is automatically set horizontal and the y-axis vertical. But at some point, students run into one of the most common textbook problems, and they are often surprised to see the x-axis drawn along the inclined ramp. So, what are the rules for choosing the directions of the coordinate axis? In mechanics, any two perpendicular lines in a plane or three in space can serve as coordinate axes. And our goal is to choose them in a way that makes solving the problem as easy as possible. Let's say in a problem, we need to add two vectors, A and B. Graphically, that's easy to do, but to actually calculate it, we need to go through a few steps. Step 1. Choose the coordinate axis. Of course, in our explanation we will assume we already know all the angles we need. Step 2. Resolve each vector into its components along the axis. Step 3. Add the components along each axis to get the components of the resulting vector. Step 4. Find the magnitude of the resulting vector using the Pythagorean theorem. Step 5. Find the direction of the resulting vector using the formula tangent of c equals cy divided by cx. We see that the number of calculations is quite large, so let's try to simplify our work. Let's place the x-axis along vector A. That way, we don't need to calculate its components. Ax is just the vector itself, and ay is 0. To find cx, we add a and bx, and cy is simply equal to by. Of course, angle B is the new angle between vector B and the x-axis. If several vectors are aligned with the axis, our advantage becomes significant. In the first example, three forces are already directed along the axis, so we don't need to calculate their components. There is, however, an even more efficient way. In many problems, we already know the direction of the object's acceleration, and therefore, according to Newton's second law, the sum of all force vectors points in the same direction. Let's place the x-axis along the direction of the resulting vector c. Then, the magnitude of c is simply equal to ax plus bx. The main advantage of this method is that we don't need to calculate the magnitude of vector c using its components. An additional bonus is that the component cy is now 0. That is, ay plus by equals 0. This gives us one more convenient equation for solving the problem. In the second problem, we know that the object's acceleration is directed along the inclined ramp, so we will choose the x-axis in that direction. So, the most convenient way to choose the coordinate axis is to align one of them with the direction of the object's acceleration. If we don't know the direction of the object's acceleration, it's worth considering choosing the axes so that the largest number of forces are directed along them. However, if that doesn't provide much of an advantage, it's usually best to set the coordinate axis horizontally and vertically, since that orientation feels more natural to us. In the first problem, if the object slides across the table, we already know the direction of its acceleration, so we choose the x-axis to be horizontal. However, if the force F is strong enough to lift the object upward, then we don't know in advance which way the acceleration is directed. In this case, choosing the x-axis along the force F gives us only one force aligned with that axis, which doesn't really justify that choice, So we will take the x-axis to be horizontal, since that orientation feels more natural to us. Let's look at the third problem. What horizontal velocity v must a ball of mass m have to move in a circle along a cone with an angle a at a height h? This problem looks similar to the second one because the surface of the cone resembles an inclined ramp. But the key point here is that when an object moves uniformly in a circle, its acceleration is directed toward the center of that circle. We also know that the magnitude of this acceleration is given by the formula a equals v squared divided by r, where r is the radius of the circle along which the ball moves. Now let's see how the optimal choice of coordinate axes can help us solve this problem. Let's choose a particular moment in time and align the x-axis with the acceleration vector at that instant. We will take the y-axis to point vertically upward. Two forces act on the ball: the gravitational force mg and the so-called normal force n, which is the elastic reaction from the cone directed perpendicular to its surface at the point of contact with the ball. Angles A and B are equal because the first side of angle A is perpendicular to the first side of angle B, and the second side of angle A is perpendicular to the second side of angle B. Let's take a look at the free body diagram. Formally, Newton's second law is expressed as N plus mg equals ma. But to carry out actual calculations, we need to break the force vectors into components along the x and y axes and write Newton's second law in scalar form for each axis. The x component nx is n sine a, and the y component ny is n cosine a. Along the x-axis, the only force acting is the horizontal component of the normal force n. Therefore, by Newton's second law, we have nx equals max, that is, n sine a equals mv squared divided by r. Along the y-axis, we write ny minus mg equals may, that is, n cosine a minus mg equals may. The projection of the force mg is opposite to the direction of the y-axis, so it appears with a minus sign. An additional bonus of our choice of coordinate axes, as we mentioned earlier, is that the ball's acceleration along the y-axis is 0, and therefore the sum of the force components along the y-axis is also 0. So, Newton's second law gives us two equations. The third equation will be a geometric relation, h divided by r equals the tangent of a. The quickest way to reach the solution is to divide the first equation by the second. Sine divided by cosine is tangent, and now we substitute h divided by r for the tangent of a. Finally, we find that v equals the square root of g times h. The result we have obtained deserves special attention. The required speed doesn't depend on either the mass of the ball or the angle of the cone. This means students might encounter this problem presented in the following, rather discouraging form. What horizontal velocity v must an unknown ball have to move in a circle on an unknown cone at a height h? Solving such a problem, we end up with 3 equations and 5 unknowns. To tackle this mathematical challenge, we can use the following method. We will temporarily assume that we know all the necessary unknowns and then begin the calculations. If we have set up all the equations correctly and the problem is well posed, then all the unknowns will either be computed or will cancel out.